Hello everyone, welcome back to this course Coherence and Quantum Entanglement by NPTEL. I am your TM Nilakshi Shanapati from IIT Kanpur, and this is the second last class or discussion session for this semester's course for this Coherence and Quantum Entanglement. I hope you guys are enjoying and you are able to grasp the course, that what is coherence, what is quantum entanglement, all of the things are clear to you at this moment. Okay, so this was a 12-week course and we are at week 11. This is 6th April 2024. This is the second last class, and this course is instructed by Professor Anand Kumar Jha, and of course you guys all know the details, but still I will formally introduce that I am your TA Nilakshi Shanapati, and this is the Saturday 5 p.m. to 7 p.m. when we discuss about the problems and we do the doubt clearing sessions. There are many doubts which you have. We try to discuss about all of them. We try to solve lots of problems such that you don't find any difficulties in solving the assignments. And of course, you guys are here to learn this course, and this is the quantum entanglement and coherence course, which is very useful in current scenario, and of course very like the world is moving towards the quantum technologies, and there are many applications of it, and there are many things to do with it, like quantum cryptography, quantum metrology, quantum information, quantum communication, everything to know and to learn about them. The fundamental things what you need to learn is coherence and quantum entanglement, and that is what we are learning here in this course. By now we on the 50% of this course we have learned detail of the coherence, because it was, and the 2-point correlation, and what are the interferometric, what are the interferometers, what are the measurements, what we actually do those things, and some I have shown you the experiments, some of the experiments, back center interferometer, several interferometers we talked about. We solved lot of problems through which we have learned about quantum lithography and all of those things. So we have developed our ground, and we have developed advanced knowledge regarding coherence and quantum entanglement eventually from day 1 to day week 1 to week 11. And there I think it in every day, in every discussion session, we used to solve at least 10 questions every time. So we have solved more than 60 questions till now, and in the last 2 weeks we'll again we'll solve the questions. I hope totally you have solved 100 questions from ourselves, and you have also solved 120 questions from the assignments. And I always mention that these discussion sessions are very useful and helpful for you guys, because here we actually discuss all of the problems which you can or may get in your assignments, as well as your quiz and your end semester examination. And I have seen several times that these are overlapping. So if you are not missing these discussion sessions, then it will be beneficial for you to gain good marks, as well as that was the part of the mark part. But as I always mention, our main purpose is to learn, and this is quite very interesting as well as difficult field, but we try to make it as simple as possible, and we have reached to this week 11 with a successful course running. So I hope everybody of you have enjoyed, but let not talk about these things more. Rather, I will just give you a glimpse of whatever the credentials you need for learning this course. As I tell each and every time when I start the course, then at that moment, so I will again go through all of them, because maybe some of you have just started before the examination to see all these videos, and some of you already are aware, but still it is no harm to get to know all of the credentials once more, and I just want that you don't lack with any of the materials such that you have problem to learn this course. That's why I mention those things again and again. So first thing first is that okay, let me go to my folder. So this is the folder where you can get this is a Google Drive folder where you can get all of the details, all of the slides, all of these documents, all of the class notes, everything there it is uploaded. So you can visit and check them whenever you are free and according to your convenience. So everything is uploaded over there. Next, the YouTube videos. If you are missing the live sessions, does not matter to you, because it is already up, it is going to upload, and the all other videos are already uploaded in this YouTube channel. Here you can get this is the YouTube channel where all the videos are uploaded. You can see from week 1 to week 10, and I can guarantee you that within the next within the half of 1 hour, or at least in the by tonight, it is of course officially available in the YouTube official YouTube channel, that is this channel. And of course in this coherence and entanglement course you get to see the announcements, and here there is a problem solving session stuff where you can access all of the problem solving session recorded problem solving sessions video links actually. So these are the video links. You can see these are all uploaded and updated in as the Excel sheet, which you can actually get it from the SWAYAM portal of NPTEL. And anyway, you know the YouTube channel, you can visit there. You can click on the bell button such that whenever I upload, you can get the notification also. Okay, so these are the things, and yes, one more thing, you have a there is a Q&A, there is 1 minute, there is a Q&A portal of this for this course dedicatedly, where you can see that there are several questions asked by several participants of this for this course, and we have tried to answer all of the questions that they asked to clear your doubts. So I request you to please ask the question, whatever the question you have in this Q&A portal, such that you can clear your doubt. And of course, if you feel free, if you want to directly contact with me, so feel free to contact with me via this email ID, which is given in this chat section. Again, another thing, if you are watching the video, then you can directly comment on the video in the YouTube chat section or comment section. I will also reply you there. So these are the platforms there where you can contact with us, and we will be very happy to help you. Alright, so this is the formal introduction of the course for this week 12, and now we will start with our regular discussion, where my plan for today is to discuss about the entanglement, quantification and connection between coherence and entanglement, where we will discuss about pure state, mixed state, for one particle, two particle, and then entanglement of formation and concurrence, which you have already gone through in your lectures, but this is just to simplify and give a revision to you. So after this quick revision, we will go to the problems. So I have again much more advanced problems for today. We'll solve the problems, we'll try to understand the problems, and once it is so after the problem solution, we will if time permits, then I will of course try to discuss about the quantum cryptography. We'll try to start the quantum cryptography if time permits today. Otherwise, we will discuss about this quantum cryptography, quantum teleportation, and we will end up the session in the next week. which is week 12, that is the last one. But our main goal for today's class is to discuss about this entanglement quantification, which you need to know that entanglement quantification is still not totally possible in the higher dimensional. So this is this is again another open question and open area where you can think about to carry forward your research. So these are the very important things that to know if you want to pursue your research in this area. And apart from that, I wanted to mention one more thing, that on the 14th of April, that is a Sunday, from 11 to 12 or 10, I think 10:30 to 11:30 or 11 to 12, I will confirm you. Most probably you will get the notification from NPTEL through spam portal, also via mail also, that we are going to have a 1 hour recap and summary session, where we will sum up all of this all of the course whatever we have done in that 1 hour discussion, and we will wrap up the course. So there will be one more class on Sunday 14th. Let me write that for you in the chat section. Sunday 14th April 2024, we will have the last last concluding discussion session for this course in this semester. Okay, the time I'm forgetting, either it is from 10:30 to 11:30 or 11 to 12. I will confirm you or in the next class, or otherwise you will anyway you are going to get notification from the from the NPTEL through SWAM portal and through via mail also. All right. So in the last discussion session, we saw how entanglement can be verified using either the Bell inequality or the APR correlations. We also summarized how two qubit states can be constructed for different degrees of freedom. You have seen them in the lectures as well as the discussion session. Although Bell inequality, violation and APR's uncertainty measurement verify the presence of entanglement, but they do not quantify the amount of entanglement present in a given 2-qubit state. The field of entanglement quantification is a very active area of research. That's what I was saying you just before this. And at this point, one only knows how to uniquely quantify the entanglement for a 2-qubit state, not a d-qubits or q-dit states. In general, there is no unique way of quantifying multi-particle high-dimensional entanglement. Let us first review the concepts of pure and mixed states in the context of one-particle system. Then we will talk about two-particle system. So let us see what is the pure state, although you know, but still let me give you a glimpse again. In situations in which a one-particle system can be completely described using a single state vector psi, the one-particle system is said to be in a pure state. In other words, if a system can be represented by a single ensemble of realization, then the system is said to be in a pure state. Your pure state can be represented as a column vector, the dimensionality of which is the dimensionality of the Hilbert space in which the system lives, and it can be written as this. For example, this is a pure state where a square plus b square equal to 1. Now it's about mixed state for one particle. When a particle system cannot be described as a single ensemble of realization and has to be described as a mixture of ensembles of realization, then the one particle state is said to be in a mixed state. Okay, what I said? Again, listen very carefully, that when a one particle system cannot be described as a single ensemble of realizations and has to be described as a mixture of ensembles of realization has to be described as a mixture of ensembles of realization, then the one particle state is said to be in a mixed state. Mixedness of a state in a given basis is directly related to the partial coherence of the state of the basis. The degree of mixedness or the degree of coherence is calculated by performing a coherent mode representation of the state, which you have already learned. What is coherent mode representation and how to do coherent mode representation? There were problems, there were discussion, there were questions, there were quizzes, there were assignments. Everywhere you have learned about this coherent mode representation. You can again visit to the concept. What was that? A mixed state is represented by a density matrix. Right? Now the coherent mode representation of the state is obtained by diagonalization of rho and can be like diagonalization of rho is the coherent mode representation. These concepts are very useful and necessary to learn to solve the assignments, and it can be represented as if the above sum contains only one term, then the state is again becomes pure state. Now this is the one particle case. What is it for pure state in two particle? Why we are interested in two particle? Because two particle is the state of bipartite state what we use for the quantum entanglement of two particles. That's why our particular interest always in the two particle or the two particle or bipartite system. So when a two particle system can be described as a single ensemble of realization, then the state is said to be pure. A two particle pure state can be written as, again if I represent it with a psi, then psi is equal to ij dij phi I a cross means the tensor product psi j b, which is this is the total two particle pure state, where phi ia and phi jb are the pure state vectors corresponding to individual particle and cross products represent the tensor product. Pure states corresponding to individual particles, and this is a tensor product. Okay, and the mixed state now. For two particles, when a two particle system can be described only as a mixture of ensemble of realizations, then the state is said to be mixed. The coherent mode representation or the diagonal representation of the state is given by rho ij mn, because now they are two like mixed state of two particles, So you can understand that there will be phi I, phi j corresponding to A and B, and again there will be m and n corresponding to A and B, and we will represent it using the density matrix format. That's why I am writing rho. This is equal to I pi psi I pi rho I. If the above sum contains only one term, then the two particle state is pure state. If the state contains more than one term, then the state is mixed and hence partially coherent. Okay. Now, the entanglement of two particles is not just about whether the two particle state is pure or mixed. It is about whether or not a two particle state is separable. If the joint state of the two particles cannot be written as a product of the states of the individual particles, then the two particle state is said to be inseparable, and the degree of inseparability quantifies the amount of entanglement. However, if a two particle state is separable, then it is not entangled. What I was saying, that if a two particle state is separable, then it is not entangled. Next, and if it is inseparable, a two particle state, then it is entangled. And we will see how this inseparability or entanglement is quantified. There are several methods for doing this quantification, but we will only look at ones which are more frequently used. Among them, there are several methods and several theoretical and experimental things were discussed to you by the professor in your lectures. So I will not go through the details, but rather I will just tell you that one of them is entanglement of formation. He has described a lot about this thing, and another was concurrence, which also there are lots of discussion regarding that. I will not go through that much details. I will not go through any experimental details also. I'll just give you a recapitulation. I'll just give you a recap of them. So the entanglement of formation, what is it? Is that the inseparability of pure states can be uniquely quantified through Schmidt decomposition. A two particle pure state can be represented like let me write rather. A two particle pure state can be represented as where phi I A and psi j B represent the state vector corresponding to the individual particle. The state psi can be represented in the Schmidt decomposed form as where Ci square equal to 1. Here phi I A and psi j B are the state vectors in the Schmidt basis. If the Schmidt decomposed form contains only one term, then the state is separable. But if it contains more than one term, then the state is inseparable. If the Schmidt, let me tell you once again, if the Schmidt decomposed form contains only one term, then the state is separable. But if it contains more than one term, then it is inseparable. As an example, you can talk about, there are several examples actually. uh, maybe maybe I can give you one example. This can be written as let me summarize the story to you. Smith decomposed means not entangled. Okay, that means since the Smith decomposed forms only one term, we see that the state is separable. This is separable as it is separable. If the Smith decomposition is not possible, that means if we cannot write it in the tensorial form, tensor product form, then it is inseparable. Hence, then we can see that there will be entanglement. Now, for this case, what I have shown, this is clearly showing that since the decomposition Smith decomposed form contains only one term, we can see the state is separable, and hence the entanglement of the state is 0. Now, in case the state is not separable, the Smith coefficient Ci squared should quantify the inseparability or the entanglement of the state. Okay, then there can certainly be several definitions of entanglement based on the Smith coefficient, but the one definition that has been adopted for the purpose is called the entanglement of formation, which is defined as E psi equal to minus of I Ci square log 2 Ci square. We note that for a separable state, we have Ci square equal to 1, therefore E psi equal to 0 as expected. And it turns out that one does not always have to find the Smith decomposition, as there are other ways to get the Smith coefficients. Let us take the partial trace of rho over particle B. Then what we get is rho A, and it is trace over B for rho. Then we can write it as equal to I Ci square phi I A phi I A. We find that the rho A is a diagonal matrix. With the diagonal terms being equal to the Smith coefficients of the pure two-particle state. So, in order to calculate the Smith coefficients, one only needs to calculate the reduced density matrix rho A of the system and take the diagonal entries. We don't need to do all the state tomography, rather just the diagonal matrix, and we can find out. Now, since Ci square are the eigenvalues of the density matrix corresponding to particle A, we find that the entanglement of formation is nothing but the von Neumann entropy of particle A. So, for a completely separable state, the von Neumann entropy of the subsystems remains 0. Now that we, because that is separable. Now that we know that how to define the entanglement of formation for a pure state, we move it to the mixed state. We know that the two-photon mixed state rho can be represented as a mixture of pure state. The diagonal representation of rho is I pi psi I psi I, that is equal to I pi rho I, is one such decomposition in which the individual pure states psi I are orthogonal. However, in general, there can be several other decompositions of a mixed state. In terms of non-orthogonal pure states, the entanglement of formation of a mixed state is defined as the sum of the entanglement of formation of the pure state mixtures that minimizes the sum. That means E rho equal to minimum of Pj E phi j. Here Pj are the coefficients of the pure state decomposition. In general, for a 2-qubit state, 2-qubit state, it is very difficult to find the decomposition that minimizes entanglement of formation. However, for a 2-qubit state, it is possible to do so, which brings us to the second measurement of entanglement known as concurrence. And concurrence is another measurement of entanglement which can be uniquely defined for 2-qubit states. And we have this. You can see here I have written, I will not go through the write up again. I have already presented that thing in the slide, such that I don't need to write all of this again and again. So concurrence is another measure of entanglement which can be uniquely defined for 2-qubit state. And this if you want to know more about this concurrence and all these things, then the original paper you can visit, which is by Wouters et al. The Wouters, W.K. Wouters, PRL at 1998, and you can see the definition of concurrence and all. So concurrence for a 2-qubit mixed state is defined as follows. Take the 2-qubit density matrix rho and construct the density matrix rho using the spin flip operation, which is like this, where sigma y is the Pauli Y matrix, and this cross is the cross product. Construct a new matrix rho cap and find its eigenvalues and arrange them in the descending order. The concurrence of the 2-qubit state is given to us maximum of 0 and minus lambda 1 minus root over of lambda 2 minus root over of lambda 3 minus root over. However, it is refined, it is like this concurrence. How it is reached to there, I have mentioned the detail of the entanglement of formation, but the detail of concurrence, if you want to know, there are several mathematics to reach to this position, to reach to this formula. So you can visit to this paper, there will be they are there. So these are the entanglement quantification, but remember, entanglement quantification can only be done in the qubit, but still it is not so generalized that we can do it for qubit mixed state. Of course, for pure state it is there, but for qubit, that is d-dimensional mixed state, it is not again is possible till now. So that is open research. You can find there are several papers, theoretical at least, but experimentally no quantification is possible till now. There are always d to the power 4 number of measurements that is required, but we want to I don't know if, of course physics will evolve, science will evolve, and maybe we'll have something. So these are the current research topic. If you are interested in this subject so much, then you can of course like if you are so interested in this subject, then you can try it by yourself, and you can like explore more and find out more research problem and find these open problems also, which are very interesting. We actually work on these things and it is quite interesting. So all right, so these are the things that I wanted to discuss. Now I will try to move towards this problem solving part, because that is the main aim of this discussion session, that we want to do the problem solving. And previous week I did not give any homework or nothing was left to carry forward in today's discussion. So today I will have fresh problems. So I think you need much more time to read the question first, understand that first, and then I will read and solve this problem. Okay. So let us wait for 5 minutes while you are reading this question and trying to understand this question. Then I will come and solve this problem. Okay, so I think you guys have gone through this question now, but let me read it and then we'll solve it. So, problem 1, it is saying that this is a setup given to you, and according to that, there is a question. 1 minute. Consider the interferometer shown above, in which y0 and d are fixed distances. X0 is the fixed distance of the signal and Adler mirrors in the balanced position. From the balanced position, the displacement of the signal and Adler mirrors are. Let me read from the first. Consider the interferometer shown above, in which y0 and d are fixed distances. X0 is the fixed distance of the signal and Adler mirror in the balanced position. From the balanced position, the displacement of the signal and Adler mirrors are represented by xs and xi. Okay, alright, respectively. Assume that the form field is monochromatic with wavelength lambda 0, that x0 greater than d greater than coherence length, where coherence length is the coherence length of the signal and Adler field, and that the coincidence time window is much smaller compared to the time x0 minus d by c. Of course, otherwise we will not be able to do the coincidence. So here we can do the coincidence, where c is the speed of the light. Finally, assume no loss, perfect mirrors, 50-50 beam splitter, and degenerate PDC, that is parameter down conversion. Now A. So through explicit calculations, how should xs and xi be changed in order to see a Hongomandel like D profile in the coincidence count rate? Okay, so you know what you need to do. You need to do the you need to calculate the delta L and delta L dash for this setup. Please try to find out delta L and delta L dash as soon as possible. While I am waiting, then I will tell the answer that what will be the delta L and delta L dash. Please, every one of you, plot the two photon path diagram to find out delta L dash and delta phi. Once you do that, then you will be able to calculate the RSI. That is the funda. I'll wait 2 minutes and then I will wait 1 minute and then I will write the things. Okay, so now I will solve it. So since it is told that x0 is greater than d greater than L coherence, and the coincidence time window is much smaller than x0 minus d by c, we find that there can be only two possible ways in which the signal and idler photons can reach the detectors in coincidence. One in which both the photons travel the shorter path, and the second in which both the photons travel the longer path. Since we are assuming no loss, perfect mirror, 50-50 beam splitter, the coincidence count rate of the signal and idler detector is given by RSI equal to C into 1 plus gamma delta L dash cos of A0 delta L delta phi. Because KT0 we are not considering. Okay. K0 is equal to, this will be 2 pi by lambda 0. For the given interferometer, the delta L will be xs plus xi plus 2x0 minus 2d, and delta L dash will be 2 into xs minus xi. You guys are all aware about the two photon path diagram by now, and you can calculate delta L and delta L dash. Those are shown to past 3 weeks to you, that how to calculate. So I am directly writing now, and delta phi is 0. Since the pump is monochromatic, we have gamma delta L is equal to 1. Why? Since the pump is monochromatic, and therefore the coincidence count rate can be written as the coincidence count rate can be written as C into 1 plus gamma delta L dash cos of 2 pi by lambda 0 delta L. Now the question A comes. It tells, show through explicit calculations how should x0 and xi be changed in order to see a horizontal dip profile in the coincidence count rate. Part A. In order to see a horizontal like dip profile, one has to make sure that one changes only delta L dash while keeping delta L fixed. I am not writing, you know that this thing. Given the expressions for delta L and delta L dash above, we find that this can be done if the signal and idler mirrors and displaced by equal amounts in opposite direction, that is xs equal to a plus x and xi equal to minus x, where a is some fixed starting distance and x is variable distance. Now the other condition that must be followed there, that is cos of 2 pi lambda 0 delta L should be minus 1. This requires delta L equal to 2m plus 1 into pi into lambda 0 by 2 pi, because cos of minus 1 equal to pi, cos inverse of minus 1 equal to pi, that's why. So again we can write this as 2m plus 1 into lambda 0 by 2, where m equal to 0, 1, 2. Now xs plus xi plus 2x0 minus 2d equal to 2m plus 1 lambda 0 by 2, and a plus x minus x plus 2x0 minus 2d equal to 2m plus 1 lambda 0 by 2, That means A equal to 2m plus 1 lambda 0 by 2 2x0 plus 2d. So in order to observe a Hongomendel D profile, the signal mirror should be first be displaced from the balanced position by an amount A and then both the signal and angular mirrors should be displaced in opposite direction by equal amount x. Since delta L dash equal to 2 into xs minus xi, so it became 4x plus 4a. We would observe the deep as a function of x and it would be centered as at x equal to minus a by 2. In order to see a Hongomendel harm profile which is given in the part B, let me read the part B question. It is telling, so through explicit calculations, how should xs and xi be changed in order to see the Hongomendel like harm profile in the coincidence count rate? In order to say a Hongomendel like harm profile, first one has to make sure that one changes only delta L dash while keeping delta L fixed. Given the expression for delta L and delta L dash above, which I have just shown in this calculation, we find that this can be done in the signal and angular mirrors and displaced by equal amounts in opposite direction, that is xs equal to a plus x and xi equal to minus x. It will be same where is a fixed starting distance and x is a variable distance. Now the other condition that must be satisfied for the observations of harm profile is nothing but cos of 2 pi by lambda 0 delta L will become 1. Okay, this requires that delta L equal to 2m pi into lambda 0 by 2 pi, that is equal to m lambda 0, where m equal to 0 1 2 and xs plus xi plus 2x0 minus 2d equal to m lambda 0 a plus x minus x. I am just substituting the stuffs xs and xi, whatever the condition should be fulfilled for of equal amounts in opposite direction, that I am that I am substituting here and further calculating, and then I will get the necessary condition for hump HOM profile. So, in order to observe a Hongomendel like harm profile, the signal mirror should first be displaced from the balanced position by an amount of A equal to m lambda 0 minus 2x0 plus 2d, and then both the signal and mirror should be displaced in the opposite direction by equal amount of x. This is the constant truth. 1 minute. Let me copy paste this thing also there. This is the second condition. Since delta L dash is equal to 4x, here delta L dash, if we calculate, then again it will become 4x plus 4a. So we would observe the hump as a function of x and it would be centered at x equal to minus a by 2. Since the two entangled photons in this setup never come together, there can be no bunching interpretation in case of the question C. What is the question C? I have already Right, I have already gone through, so I hope you have already gone through the C. I have given enough time to you to read it, but let me go through the question once. Question, it is saying, does the fundamental deep is in this interferometer have a bunching interpretation? Since the answer will be the since the two entangled photons in this setup never come together, there can be no bunching interpretation in this interferometer of this fundamental profile. Okay, so this is the problem one. Now we'll discuss about this problem 2. Please go through the problem 2. I am giving you a few minutes. Please go through it. Okay, so now let's start solving this problem. It is saying consider the two photon interference setup shown below. Now, A. Assuming that the coincident detection system is much faster than the delay time x by c, calculate the coincidence count rate RSI and the one photon count rate RS and RI in terms of x. But you know first what you need to do. We'll follow the steps. We need to find out del L, delta L dash and all those things. So to solve to get the RSI, and then of course we need to calculate the RS and RI from this RSI. This is a one photon count, and we already have learned how to do that from the previous day's discussion. So I will follow one by one all of them, but let me show you the figure first, like how to find out the delta L and delta L dash for this case, because for the previous case I have not shown you, because I just wanted to do it by yourself for that problem, because otherwise I have shown for all of the problems that what will be the two photon path diagram. So again I am showing, giving you the answer that what will be the two photon path diagram for this. You just please follow that. If it can either go in this direction what I am showing in this cursor, and you can see that ds and di are there, or otherwise it can go in this direction, that is directly this is directly transmitting through the fast beam splitter and going to transmitting again to the beam splitter, which is showing with the 2. And if you find the phi s1, phi i1, phi s2, phi i2, delta L dash, delta phi, then you will find this. So these are the stuffs. And next I can write, you can see that for the first case the delta L will be x, delta L dash will be 0, and delta phi will be 5 pi. And for the next part and for the and otherwise it is possible when we are detecting from ds and di, when we are doing the RSI calculation, but we need to calculate the RSS dash and RSS dash RSS, because we want to calculate the one photon coincidence. One photon coincidence is also possible if it is coming through the one is reflecting and another is transmitting, and it is detecting both towards this ds and ds dash if there would have been one another ds dash detector. And that is similarly true for the this part 2 also. So all of these are needed for this to calculate the one photon. So first let me write the first let me do it step by step. First, since the coincidence detection system is much faster than the time delayed between the two arms of the interferometer, there will be only two alternatives that will contribute to the coincident detection. For these two alternatives, delta L is equal to x and delta L dash equal to 0, that is shown in this. And delta phi will be 5 pi. Now therefore the coincidence become RSI equal to 2R 1 minus gamma x cos k0 x, and here we have made one other assumption, that x is less than coherence length of the pump. Then for calculating the one photon count rate RS, what we need to do is that RSI plus RSS dash, if there would have been another detector S dash, then we can find, then we can refer to the part C, where we can again del L equal to x, delta L dash equal to 0, but delta phi now is 6 pi. Therefore we can calculate RSS dash equal to 2R1 plus gamma x cos k0 x, and thus RS become RSI plus RSS dash, which becomes 4R, that means constant and no interference pattern. So we see that the one photon count rates of the two detectors do not show any interference pattern. Alright, now come to the part B. It is saying Describe where do the entangled photons go when minima are observed in the coincidence count rate. A very nice question. Describe where the entangled photons go when the minima are observed in the coincidence count rate. Note that this setup is an alternative way of doing quantum lithography as described in the previous classes one question. I talked about quantum lithography from one question, and this is another setup through which you can do the quantum lithography. And so you need to make another okay, so you need to give the answer that when the minima is observed, then what happens to the entangled state. The answer is when a minimum is observed in the coincidence count rate, the entangled photons both leave through either one of the output ports of the interferometer. That's why you do not see the, that's why you do see the minimum. So what is the answer? When a minimum is observed in the coincidence count rate, then it the actual thing what happens is that the entangled photon both leave through either one of the output ports of the interferometer. Okay, so that was the question, and this is the answer. And part C, it is saying design another experimental setup that would keep gamma dash till L dash 1 and that can be used for quantum lithography. You guys please try it by yourself, but I can say that it will be by using a prism. So you can take some time. Again, I will give some time to find out this very interesting problem and do it by yourself. This part C, design another experimental setup. You can design it by yourself. Try to think that how you can make it a quantum lithography setup. Okay, so I will show you the setup what we have made. So but first you guys give a try at it. So I will wait for a few minutes you to try. Okay, so now I will show you the other setup possible. This is the other setup that you can, that is possible. Why because in this another this setup, it is possible to make two photon known state, and we can see that the state of the two photons can be set up as like 1 by 2 to 2002. That means we can do the lithography with it. I have also shown this to you in previously in one question also. That's why I always tell you to follow the questions more appropriately, such that you are able to do solve another problem. So this was the question. Now we will solve another question, problem 3, which is even more intense. So we have 5 part of this, and then there are some more problems, problem 4, problem 5. We'll try to solve this today. Let's see what happens. So problem 4, it is telling that let us consider the production of entangled photon using parametric down conversion as described in the figure. So we, in the class, means in the lecture, we derived the expression for two photon state to be psi tp like this for the special degree of freedom. Now part A, it is saying within the assumptions of collinear down conversion and paraxial approximation, show that the electric field operators at the two detectors are given by this. So let me solve the problem. So the signal electric operator of the detectors can be written as, the signal electric field operator at the detector can be written as ES plus RS equal to dq AS cap q e to the power I q dot rho s minus kz z. We consider only the collinear down conversion and thus make paraxial approximation. Therefore, we can write kz as root over of k square minus q square, where it can be written as ks into root over of 1 minus q square k square, that is again equal to ks integration of 1 minus q square by 2 ks square, which is again equal to, I can write ks minus q square by 2ks. So substituting this in the above equation, which is this equation, and doing a similar approximation for the idler also. So first let me write the for the signal what it will be, then we will write for the idler. This is IKS jet dq AS cap q e to the power I q dot rho s minus q square z by 2 ks, and for the idler field it will be e to the power I k I z integration dq dash a I cap q dash e to the power I q dash dot rho I minus q dash square z by 2 ki. So that is what it is told, where q square equal to q square, q dash square is equal to modulus of q square, k is equal to ks omega s, and ki equal to modulus of ki omega y. That you guys know by now. So you needed to prove this, that within the assumption of collinear down conversion and paraxial approximation, show that the electric field at the operators at the detectors become this. So just you need to write the electric field operator and take the paraxial collinear and paraxial approximation, and we'll get this. So part A is proved. Now part B, it is saying next take k is equal to ki equal to equivalent, k is equivalent to ki equivalent to k0 by 2, where k0 is the central wave vector magnitude of the pump field and k0 is the central wave vector magnitude of the pump field, and consider the one dimensional version of this problem so that rho tends to x. Also take the pump to be completely spatially coherent Gaussian beam that is given over there with the v, where omega 0 is the pump beam waist, so that the two photon probability amplitude psi tp xs xi is equal to vacuum of this ei plus es plus, that is the expectation of that is a probability amplitude which is given by psi tp xs si, like this, where omega z is equal to omega 0 square plus 4z square by k0 square omega square whole to the power half is the beam waist of the pump at z equal to z and is z dependent constant. So we need to do this part 2. Let's do whatever it is told to you. So part B, for the one dimensional version of this problem, we have psi tp you guys know these steps, that's why I am not explaining. This is what just we have done now, but right now I am doing in the 1D. Okay, so we need to find the two photon probability amplitude psi tp xs xi equal to vacuum. It is also given to you. Using a cap s k equal to delta of k sx minus k sx dash and k ix dash equal to k ix equal to delta k ix minus k ix dash, and integrating out the Dirac delta functions we get I will not write this again and again. Let me take this. So this is equal to a to the power I k s plus k I z integration minus infinity to infinity d k sx d k ix v k sx k ix exponential I k sx k ix xi minus I k x square 2ks plus ki x square 2ki. Now assume degenerate down conversion, that is ks equal to ki by k equal to k0 by 2, which is given to you. Also substitute the Gaussian field, that is v ksx kix equal to exponential minus omega 0 square ksx plus kix square by 4. These are given to you. So if you do the same operation now again, let me write this again. Then we'll find this term as So now we'll solve the integration, and we will use the Gaussian integration formula that we already have derived in the earlier problems also. That e to the power minus infinity to infinity integration minus infinity to infinity e to the power minus alpha x square plus beta x dx equal to pi by alpha whole to the power half e to the power beta square by 4 alpha. So if we use that and substitute for the first part of the integral, then what we will get is and the second part. Second integral. So where alpha is, if you do the integration, first integration and substitute, then you will be able to get that what is alpha. Alpha will be Iz by k0 plus omega 0 square by 4 from the standard Gaussian integral, whatever we are using for the codes several times. Now using the same Gaussian integral formula as above, as we are using for the first integral, now we will use it for the second integral. Okay. So now this first part is common. And for the second integral, it will become now if you further calculate, then it will become this. This can be further simplified, and if you simplify, then you will be able to get this form whichever is given in this equation. Whatever it is given over there. At wz is given to you, that is a beam, wz is w0 is a pump beam waste, and wz is given to you omega 0 square plus 4z square by k0 square omega 0 square to the power half is the beam waste of the pump is given to you. Okay. So now part C. Let me read the question. Finally, show that the two photon coincidence probability 2 within an overall z dependent constant is rxs xi equal to psi tp xs xy whole modulus square is this equal to, it will be equal to this. Fine, let's do that. Sorry, we can write it like this because it is a complete state, and we can use the this is a complete basis. This is a dagger, and this is this. It will become this. If you calculate further, if you you need just the modulus part, and everything will whichever had the I part, that will be blow up, and that's why it will be end up with, it will be just the a is some constant, where the before like whatever it is there, a 16 pi square, and if we take the square, whatever the stuffs are, that will be there, and whatever has a to the power I terms, those will be clearly go out, blows up, because they are plus minus both. And now only we will left with this xs plus xi whole square by 2 omega square z, which depends upon the beam waist. So this is a thing that we need to prove, and you got that. Now it is told, plot the above two coincidence probability and describe it. So I have already plotted this. This is a plot that you will get as a function of RSI as a function of Sx and Xi, and it's what's the density plot of the probability distribution. The plot is for lambda equal to 800 nanometer, omega 0 equal to 2 millimeter, z equal to 1 meter. We find that at particular z, given that the signal photon is detected at some xs, the range over which the adder has a finite probability of getting detected is wz, which is this is the correlation width of the down converted photons. We can find that this correlation width is equal to the width of the Gaussian beam of z. As z increases, the omega z increases, and we found the position correlation width increases in the same proportion. So this is the explanation of detailed explanation of that of the question. It is showing that, telling that plot the above two photon coincidence and describe it. So this is all. Now we will go to the problem 4, which is this. But before, just digest this whatever we have told and shown to you, and then I will come back to that problem 4. Okay, so let's do the problem 4. It is saying consider the following two particle wave function which is given at psi x1 psi equal to this, and where psi k x2 and uk(x1) are the function corresponding to the second and the first particle. Now if the first particle is measured to have momentum h bar k0, what is the expectation value and the uncertainty of the moment of the second particle? This is already shown to you, so I would like that if you try to think it out by yourself that how to solve it. I will definitely do this, but please think it once, that you have already we have already shown this to you in the previous class itself. So do you remember? So now I mean I'll just tell you that what will be the thing, that if psi k(x2) is equal to this and uk(x1) equal to this are the eigenfunctions of momentum operator corresponding to the two particles of eigenvalues h bar k and h bar minus h bar k respectively, then therefore upon momentum measurement, if the first particle is found to have momentum h bar k0, the second particle is guaranteed to have the momentum value of h bar k0, because we have done this and we have learned this from the quantum entanglement, right? So without doing anything, you can write for the problem A, that part A, that if the upon momentum measurement, if the first particle is found to have momentum minus h bar plus h bar k0, then the second particle is guaranteed to have the momentum of minus h bar k0. Thus the expectation value of momentum of the second particle is minus h bar k0 with uncertainty being 0. That will be the answer. And part B, it is saying write psi x1 x2 in terms of the position eigenfunctions of the two particles. This thing is already shown to you. Let me just show you. If I have this till now, this the answer will be just this. Whatever you can see in your part B, answer is given in the screen. This I solved for in the previous week 10. You just can understand how the answer is this. Now it is saying explain how the two particles are correlated in their position measurements. So the answer will be for the above two state photons. Let me go to that slide again. This slide. So the answer is for the above two photons, given two photon state, which is Vx x1 equal to delta x1 minus x, is the eigenstate of the position operator x1 of the first particle with eigenvalue x, and phi x x2 is equal to delta x minus x2 plus x0 is the eigenstate of position operator x2 of the second particle with eigenvalue x plus x0. With the second particle with the eigenvalue of x plus x0. Let me tell you once again that for the two photon state, for the first particle 1, the eigenvalue is x, and for the position operator x2 with the second particle, the eigenvalue is x plus x0. Therefore, upon position measurement, if the first particle is found to be at the position x, the second particle is guaranteed to be found at x plus x0. That will be the answer. So this is your 3 questions, 3 part of this problem 4, which you already know. Now this problem 5. And I will just tell this problem and give you as homework problem. Give you these as homework, and we will start next class with this problem, which is telling that suppose the two photon wave function is in the position basis is given by psi x as xi is given like this, which is just the Gaussian shell model kind of thing, The corresponding two photon wave function in the momentum basis is like this. Now calculate the conditional uncertainty in the position of the signal photon, calculate the conditional uncertainty in the momentum of the signal photon, find out the condition in terms of omega and sigma such that the above two photon wave function violates the conditional Heisenberg uncertainty principle. So I would like that you guys try it once at your home as a homework, and then we'll solve this in next class and last class, and we'll of course again solve some another problem, and we'll start discussing about the quantum. I had the plan to discuss about quantum cryptography. I have also shown I have also the slide, but today time did not permit us. We had lot of things to discuss and solve, so we'll start from the quantum cryptography in the next week, and then quantum teleportation, and we'll end up the session with some problem solving, and finally we'll end the whole this course on the Sunday. So there is and I have the necessary things I always used to mention again and again, so I will not mention today at the last again. I hope you remember everything. So this was the week 11, and we signing off for today. So see you guys next day, next week at the same time for further discussion again, or for the week 12. Bye.